In this experiment, you're going to be graphically verifying the predictions of a torque equation. So torque is the rotational equivalent of force. So just as you can have a force equation where all the forces are balanced and that means you have no acceleration, you can also have a torque equation where all the torques are balanced and you therefore have no rotation. Specifically, what we're going to be doing is we're going to take a ruler and we'll attach our sensor to it with a rubber band or a piece of string. And then we're going to hold the ruler parallel to a 45-degree line and ensure that we're pulling at 90 degrees to the ruler. And then we'll just measure the force while holding the ruler in this position. Then we'll do it again for a different position. So again, we make sure the ruler is parallel to the 45-degree line, and we just make sure that this angle here is 90 degrees. And again, we would measure the force for a couple of seconds while holding the ruler in this position. And then we can move down to another position and do the same thing. Now, one thing that's going to be a problem is that you'll notice that if I get too low here, I stop being able to hold the ruler in the correct position. So for example, when I try to go to 90 degrees, here, the ruler starts slipping. So I can't get it to 45 degrees parallel to the line and also have 90 degrees on the force. So the reason why that's happening is that we need more friction right here. And there's two ways to get more friction. So first of all, if you have a plastic ruler and a metal ruler, use the metal one. It weighs more, and that means you've got a larger normal force down here and therefore a larger friction force. However, you can use a plastic ruler if that's all you've got. You just need to come up with a different way to put more friction here. So for example, I've got one of these non-stick rubber pads for the kitchen. These work really, really well. So this gives me lots of friction here, and I don't get any slipping of my ruler. If you've got a repair kit for a bicycle tire, the little piece of rubber in that would also be a good thing to use here. It'll give you lots of friction. If you don't have that sort of thing, then another thing that works surprisingly well is you take a book and you wrap a t-shirt around it or some other piece of rough cloth, and that also is going to give you more friction. Not as much as a rubber pad, but it does help. So I do recommend that if you have a metal ruler, you use that preferentially, and if at all possible, you find some way to make this surface down here high friction. Now you will find that there are still limits to how far down you can move the string or the rubber band and still be able to hold the ruler in this position without it slipping or swinging. So I do recommend that at the very beginning, before you start, that you explore a little bit up and down and see what range you're able to take data with and how far is too far, such that the ruler will start swinging out of alignment. So explore the range and just see what the minimum R value from the point of support, the pivot point, to the point where you apply the force is. Find out what the minimum R value that you can take data from is, and then you'll take data at that point. You also want to take data at the farthest point that you can get away with, and then you need 6 to 8 data points to get a good graph, so you can choose the intervals in between that. But you'll get the best possible graph if you can arrange for the largest possible range of values here, and that is mostly determined by how much friction you can add down here. You only need to obtain 2 values for your graph. It'll be the distance r from the pivot point to where you applied the force, and the force that you measure with your sensor at this point. And as I said before, you just hold your ruler in this position and take data for a few seconds with the force probe. Now, something else to be careful of is that the forces you're going to be measuring are very small. So make sure that you zero your force probe before you begin. In fact, you may want to zero it a few times while you're taking data. Now, the slope of your graph is going to be compared to a theoretical value, and so you'll need to get some other things off of your ruler in particular. So one of them is you need the true length of the ruler. So this is a 30-centimeter ruler, but then I've got little bits of plastic on the end here, so I would need to measure how big these are and add them to the 30 centimeters in order to get the true length of my ruler. And likewise, when I'm taking data, if I've got my force, say, applied here, I need to remember that I've got a little bit of plastic down here, so I need to add this distance to my measurement up here. Another thing you're going to need is the weight of your ruler. So if your ruler has a hole in the end of it like this one does, then what you could do is take your sensor and hook a paper clip or something on there, zero your sensor with the paper clip in place, and then you can hook this guy on here. and measure the weight of your ruler that way. If your ruler does not have a hole in it like that, however, then you might consider doing something like this instead. You can thread an elastic band through it, and again, zero your sensor with the elastic band in place, and then you can use the elastic band as kind of a cradle that you can then suspend the ruler in, so you can measure the weight of the ruler that way. So I'll leave it up to you to figure out a way to do this. So you'll need the length of your ruler and the weight of your ruler for the theoretical values, and then for your experimental values, you'll suspend your ruler by your string or your rubber band, and again, for every data point, you're going to arrange that the ruler is parallel to your 45-degree line and that the angle here is 90 degrees, and you will take measurements for a variety of R values, and you'll try and go as far down the ruler as you possibly can without the ruler starting to swing out of alignment or slip. Now at this point, I assume that you know how to take forces and how to estimate all the uncertainties that you'll need to, so I'm not going to show you how to take data. I'm assuming that you can do this at this point. One thing I will note, though, is that this is a bit of a fiddly experiment. So if after you've taken all your data and graphed it, you find that you have one or two data points that do not fall on the line, that is, that your graph is not linear with an uncertainty, you should be willing to go back and double check those values, because it is possible and even quite likely that you'll have one or two that just need to be remeasured in order to give you a linear graph. And I will also again stress the importance of zeroing your sensor, just because the forces you will be measuring are quite small.